Hello everyone, my name is Jenny. The topic I am presenting today is a model of AGN feedback, observation of carbon monoxide line emission from the massive galaxy in the center of Phoenix cluster. The original paper I read is ALMA observations of massive molecular gas filaments encasing bubbles in the Phoenix cluster. The paper is written by H.R. Russell and McDonald's, etc., and it was published on December 16th, 2016. I would present a background summary on AGN feedback mechanism, followed by a brief introduction on the target galaxy in the Phoenix cluster. Then I'll discuss the observations on the central galaxy and how it demonstrates a mode of AGN feedback. At last, I will emphasize some important takeaways of the original paper and the presentation. So first of all, I want to talk about some background information of the AGN feedback. AGN, or active galactic nucleus, is a compact region at the center of a galaxy that has a much higher than normal luminosity, for which the emission has been observed in all radio, microwave, infrared, optical, ultraviolet, X-ray, and gamma ray wavebands. In other words, in all of the wavelengths. The observed luminosity is linked to the accretion of matter by a supermassive black hole at the center of its host galaxy. One way that the dramatic supermassive black hole located at the center of its host galaxy output its energy is by radio jets that can drive ionized and molecular gas outflows. A simulation of AGN jet propagating through clouds, made by A.J. Limaye, is displayed on the screen. The orange part demonstrate a spherical distribution of clouds, like over here, around the center of the galaxy. And the green and blue parts from the center of the galaxy all the way to the top and actually to the bottom as well, demonstrate the AGN jets that propagate through the clouds. Another simulation that I found can better visualize a AGN jet propagating through a clumpy, inhomogeneous two-phase medium consisting of dense clouds and a hot background. As you can see, in the blue color is the gas that floods and channels through the Perrault's interstellar medium and ablates and accelerates the dense clouds in the process. So one of the things that we need to pay attention is that the jets shown in blue and cyan is relatively clear, and the interstellar medium that is shown in the red, yellow, and green colors are relatively hotter, which is quite uh, different from what we would expected the color to be. So go back to the PowerPoint. Um, by many years of different studies and research, astronomers have linked the formation of radio bubbles in the hot X-ray atmosphere of the host galaxies to the AGN jets and molecular gas clouds that is either directly lifted by radio bubbles from the center of the AGN or is formed via thermal instabilities induced in low entropy gas lifted in the updraft of the bubbles can form extended filaments along the peripheries of the radial bubbles. For those molecular clouds that have velocities slower than the stellar velocity dispersion in the massive galaxies and lie below the galaxy's escape velocity, the cooler clouds could eventually fall back into the center of the galaxy and fuel both starburst and AGN activities, in which it will form a self-regulation process that is called the positive AGN feedback. On the contrary, if the molecular clouds are powered enough to escape the galaxy into outer space, as the previous video pretty much has demonstrated already, the host galaxy will lose its fuel and would slowly transform from a gas-rich galaxy into what is called a red and dead galaxy at some points in the future. And this process is called the negative AGN feedback. So the reason we want to study the AGN feedback is that it is one of the most powerful and significant mechanisms in galaxies formation and evolution. And the observations and analysis on the target galaxy I'll talk about in a minute show that the target central galaxy in the Phoenix cluster is a distinct mode of positive AGN feedback. Here, I want to give a brief introduction of the Phoenix cluster and its central galaxy, which is the target galaxy we'll study. The Phoenix cluster, and by the way, is shown in the background picture, is a type 1 galaxy cluster located at the southern constellation of Phoenix. The brightest cluster galaxy, which is the central galaxy, holds an active galactic nucleus, which is powered by a central supermassive black hole. The dramatic massive starburst, about 500 to 800 solar mass per year, hosted by the central galaxy, is amongst the largest found in any galaxy below a redshift of z equals to 1. So if you don't really have a clue what that sounds like, you can compare it with the star formation rate in our own Milky Way galaxy, which is approximately 1 solar mass each year. Now, let's look at the observation and analysis on the target galaxy. The left-hand side of the picture is a carbon monoxide intensity map for velocities from 0 to 480 kilometers per second, including both the central peak, which is around the black cross in the middle over here, and the three extended filaments toward northwest, southeast, and south, respectively, displayed in the color of cyan, green, and yellow. The dashed white contours at the top and bottom of the screen shows the X-ray cavities. The right-hand side of the picture is a photograph taken by Hubble Space Telescope at the same field of view as the left-hand side intensity map has shown. Clearly shown in the intensity map of carbon monoxide, the X-ray cavities, quote unquote, block the molecular clouds way of entering the region. As you can see in this on screen, There's no detected carbon monoxide in the dashed region. The masses of these three filaments are calculated to be 0.5 times 10 to the power of 10 solar mass for the northwest filament and 0.3 times 10 to the power of 10 solar mass for both the northeast and south. Oh, actually, sorry, southeast filaments and the south filaments. Um, the total molecular gas mass is approximately 2.1 plus or minus zero point 0.3 times 10 to the power of 10 solar mass in the entire galaxy. Therefore, the structure of massive filaments, in a sense of surrounding the X-ray cavities, or in a way of wrapping around the X-ray cavities, indicate that the structure of the largest molecular gas reservoirs located in the most massive galaxies is shaped by the expansion and trajectory of the radio bubbles. This picture shows the velocity line center for filaments and central peak separately. The central the spectral fitting analysis reveals that the molecular gas structure has two distinct velocity components, filaments and central peak. The filament components on the left-hand side has greater range of velocity in the line of sight and smooth velocity gradients along the length, while the central peak component on the right-hand side has lower velocities compared to the filaments. Also, on this page, the filaments component has a narrow full width at half maximum values around 100 to 200 kilometers per second, while the central peak component on the right hand side has a much higher full width at half maximum values around 300 to nearly 600 kilometers per second. Moreover, analysis on the velocity dimensions show that the velocity gradients across the nucleus appears to lie perpendicular to the velocity gradients along the northwest to southeast filaments. Above all, these differences in the velocity properties indicate that the molecular gas cools and decomposes from the hot atmosphere and falls toward the galaxy center, providing the fuel for AGN positive feedback mechanism. So, in conclusion, half of the total molecular gas or molecular mass reservoir at the center of the Phoenix cluster lies in the extended three filaments that wrapped around the X-ray cavities that are inflated by the radio jets powered by the supermassive black hole at the center of the central galaxy, which proves that the formation of the molecular gas filaments is linked to the relativistic jets from the AGN activities. Also, the velocity gradients of different components and the width of the lines imply that the molecular gas does not have enough velocity to escape the galaxy, and therefore they eventually fall back into the center of the galaxy and causes the extreme starburst at the center, which we've mentioned at a few pages before, that the starburst in the center of Phoenix, in the galaxy of Phoenix cluster, is 5 100 to 800 times um, faster than the star formation rate at our own Milky Way galaxy. And also, um, this molecular gas keep fueling AGN activities that maintain the AGN feedback mechanism. So, to further visualize the entire mechanism, I will directly draw on my screen so that you can see the self-regulation process. So first of all, there are a great amount of cold molecular gas at the center of the galaxy. Cold at the center of galaxy. That can cause star burst and AGN activities. The AGN activities can take place in the form of quasar radiations, and which we're not going to talk about today, and relativistic jets. And the radio jets will contribute to form the radio bubbles in the hot X-ray atmosphere. And molecular gas filaments would form around the radio bubbles. So in a way of filament of molecular gas. And the way the molecular gas can form are by directly lifted by radio bubbles or via the thermal instability. So if the filaments do not have enough velocity to escape the galaxy, the massive molecular gas will eventually cool down and then fall back all the way to the center of the galaxy. And by doing so, it actually forms the loop of AGN positive feedback. So here I listed all my references for the presentation, and the main resource is the original paper written by H.R. Resvell. Thank you for listening.